So, we have been discussing about the gravity gradient satellite. So, we will continue with that. So, if you remember in the last lecture, we have derived equations for the first Euler dynamical equation in terms of Euler angles and the second Euler dynamical equation in terms of Euler angles. So, those equations we have written like this one and this one. So, we will refer back to this equation again. So, we go to the third equation, which is I 3 times omega 3 dot minus omega 1 times omega 3 omega 1 times omega 2, the same term as related omega 1 appears here in this place. This equal to on the right hand side 3 omega 0 square, then I 1 minus I 2 times C 1, C 2 and 3 3. So, C 1 3 times C 2 3, this we have to insert. So, go back here in this place, C 1 3 is minus S theta 2. So, this is minus S theta 2 and C 2 3 is S theta 1 C theta 2, S theta 1 C theta 2, S theta 1 C theta 2. So, if you look here in this quantity is of second order, okay, which will be something like minus theta 2 times theta 1 and this is 1. So, this will be around 0. So, this term on the right hand side it drops out. So, this is equal to 0 for the small angular perturbation and then simply we have to insert here omega 3 dot. So, omega 3 dot again we have to go back and find out those values. Omega 3 dot, omega 3 is here theta 3 times plus omega 0 theta 1. So, theta 3 dot plus omega 0 theta 1 minus I 1 minus I 2 times omega 1 omega 2. So, omega 1 and omega 2 again we have to pick up from this place. Omega 1 is theta 1 dot omega 0 theta 3 theta 1 dot minus omega 0 theta 3 and omega 2 dot is theta 2 dot minus omega 0. This is theta 2 dot minus omega 0. This is your omega 2. So, the right hand side is set to 0 and here because we are taking the derivative of this, we are writing as omega 3 dot. So, we have to put a dot here, we have to put a dot here. I 3 times omega 0 times theta 1 dot 1 minus I 2 and expand this term as earlier we have done, theta 2 dot minus omega 0 times theta 1 dot minus omega 0 theta 2 dot times theta 3 and last term will be minus minus plus omega 0 square theta 3 and this equal to 0. Now, looking back, this term is 0 being of second order and this term is also of second order. So, this is also 0. So, we are left with this term and this term. So, I 3 times theta 3 double dot theta 1 dot minus I 2 minus omega 0 theta 1 dot plus omega 0 square theta 3, this equal to 0. So, whatever the terms we can combine, we will combine here. Okay. If we take the write it this way. So, what we want to do that this term we can take it outside. So, this minus that makes it plus. So, we can write this as I 1 minus I 2 plus I 3 times omega 0 theta 1 dot. Okay. This term from here to here, and thereafter we are left with this term. So, that gives you I 1 minus I 2 times omega 0 square theta 3 is equal to 0. So, this is our equation C. So, these are the three Euler's dynamical equation, but now it is written in terms of the Euler rates and the Euler angles. So, benefit is that if as I have told you earlier that quite often we look for how the body is rotating. So, if we are looking in terms of the body components, that is omega 1, omega 2, omega 3, we can visualize nothing, but if we look the same thing in terms of the Euler angles, then we can visualize how the satellite is moving. And for that reason, we have expressed it in this form, and there we are assuming that the Euler angles are small and Euler angular rates are also small, and therefore, the approximation can be done. So, under these conditions, how your Euler's dynamical equation it looks like, then whether using this the question is that using this what we are going to get, okay, how we are going to get benefited. The key thing is that we can look into the system stability. How do we look into the system stability? We always linearize a system, and then we look for whether the system is stable or not stable. This is what we do most of the time. We do the analysis in terms of eigenvalues. Okay. If the eigenvalues are lying absolutely in the left half complex plane, the system is stable, dynamically stable. If it is lying on the imaginary axis, so still we say this is stable, but it is called the actually marginally stable. This kind of system, it is a in reality, in the physical reality, this kind of system also considered as unstable, because once the noises, the system absorbs the noise. So, that noise is basically the absorption of energy. Okay. So, and because of that the system may become unstable. So, the system which are marginally stable, still it is considered as stable, but in from the physical reality point of view, this kind of system will ultimately it may create problem. While if the eigenvalues are lying in the right half complex plane, so then the system is completely unstable, there is nothing to do. So, if, like here I can say that x dot equal to f x. Okay. So, I can linearize the system and I can write it like this, dou f by dou x times delta x. Okay. So, this is a linearized system. Let us look into this place, and if you write it in this format, that this is a vector and x tilde is a vector. So, therefore, we can put a tilde here to indicate this is a vector, this becomes a matrix. And in this format, this is nothing but delta x dot tilde, this equal to a times delta x tilde, and you know that this is of the form x dot equal to a x, which is a linear differential equation. And this equation, and how do we analyze it? As I have told you, we get the eigenvalues of this, get the eigenvalues of A. If you give command E I Z A, so it will list you the eigenvalues of matrix A, and from there you will be able to know whether your system is locally stable or not. While we do like this, we just look around the equilibrium point. Okay. And how do we define the equilibrium point? We set x tilde dot equal to 0 and look into the find out the equilibrium point. So, about the equilibrium point, we are linearizing the system and then looking into its stability. Okay. Now, once we have got these three equations, so then it remains to study the stability of the system. So, we will have to accumulate all the three equations in a single place. So, we have the first equation we have written as theta 1 double dot minus So, the first equation we have written as theta 1 double dot minus omega 0 plus I 3, and here there was I 1. So, this I 1 I am eliminating from this place, and this I 1 I will put here in this place. And then we have the term of course theta 3 dot. So, go back, verify this, we are writing it correctly. I 1 times theta 1 double dot I 1 minus I 2 plus I 3 omega 0 times theta 3 dot, omega 0 times theta 3 dot, omega 0 I have written here in this place. And then the next term, this is 4 omega 0 square omega 0 square theta 1 4. So, I am writing it in the beginning, then I 2 minus I 3, I 2 minus I 3, and this also will get divided by I 1, because the I 1 I have pulled up from this place to this place, and then this is multiplied by theta 1, and this is set to 0. Okay. So, this we can brief as 1 minus I 2 minus I 3 divided by I 1 times theta 3 dot plus omega 0 square I 2 minus I 3 divided by I 1 times theta 1, this equal to 0. Let us say this is equation number 1. Here k 1 equal to I 2 minus I 3 divided by I 1. Similarly, the pitch equation, this is your pitch equation, this we can write as theta 2, here itself let us first write and then we will write on the next page, I 1 minus I 3 divided by I 2 times 3 omega 0 square theta 2, this equal to 0. So, theta 2 double dot I 1 minus I 3 divided by I 2, theta 2 double dot plus I 1 minus I 3 plus I 1 minus I 3 divided by I 2, then this 3 factor is there, 3 omega 0 square theta 2. So, this 3 factor will put 3 omega 0 square theta 2. So, we will put it like this, 3 omega 0 square theta 2, this equal to 0, and this will write as k 2, and quite often it is also written as k I, which is I 1 minus I 3 divided by I 2. So, this can be written as theta 2 double dot plus 3 omega 0 square k 2 times theta 2, this equal to 0. This is your equation number 2. What we can look at, theta 2 is the pitch angle. Okay. So, I will explain you why I am calling this as pitch. Earlier also I have told you, here you can see that in this first equation the theta 1 and theta 3 both are involved, okay. While here in this only theta 2 is there, theta 2 double dot and theta 2. So, this is not coupled with the other displacement or other Euler rates. So, this implies that the pitch motion is decoupled from the yaw and roll. Yaw and roll, it is related to, this is related to theta 3 and this is related to theta 1. We will return back to this part. Okay, first let us wind it up. And then theta 3 dot, finally we have to write. So, theta 3 dot, we go back into the equation, theta 3 dot is here. So, this theta 3 dot, let us first write here in this place, theta 3 double dot, this equal to I 1 minus I 2 plus I 3 divided by I 3 theta 1 dot I 1 minus I 2 times omega 0 square, and of course, we have to divide it here. Slash I 3 omega 0 square, this is in bracket, times theta 3, this equal to 0. Okay, so, we have theta 3 double dot plus I 1 minus I 2 and all these quantities are there. So, we can rewrite this as I 3 divided by I 3, this will be equal to 1, okay. And then this I 1 minus I 2, we can write this I 2 minus I 1. Okay. We can write it like this. Okay. It is the same thing. If we look here, so if we multiply it like this, this will get reduced to I 3 minus I 2 plus I 1 divided by I 3. So, we can write in this way, it is a little advantage that we will see how it eases the thing, omega 0 times theta 1 dot, omega 0 times theta 1 dot, and then the last term I 1 minus I 2 slash I 3. So, this will write as I 2 minus I 1 plus I 2 minus I 1 divided by I 3 times omega 0 theta 3. So, omega 0 we can put in the beginning here itself, is equal to 0. Now, going back here, I 2 minus I 3 divided by I 1 we have defined as k 1. Okay. So, similarly, I 2 minus I 1 divided by I 3 will define this as k 3. And if we define this quantity, then we can write this as 1 minus k 3 times, and omega 0 again I will put it here. This is plus omega 0 times here theta 1 dot here, this is there is omega 0 square, this particular term. Okay. One page extra blank page has appeared. So, here this quantity is omega 0 square, 2 extra blank pages have turned up. So, minus omega 0, this we have written as I 2 minus I 1. So, this gets reduced to plus, and this omega 0 square is there. Okay. So, here omega 0 square, this square we have to put, and this term is k 3 times theta 3, this equal to 0. So, this is the equation number 3. So, combined together, now we have the, we can summarize the whole thing 1 minus k 3 times theta 1 dot plus omega 0 square k 3 times theta 3, this equal to 0, then theta 2 double dot plus 3 omega 0 square k 2 times theta 2 plus 3 omega 0 square k 2 times theta 2, this equal to 0 and theta 2, and this one last one. So, theta 1 double dot minus omega 0 theta 1 double dot minus omega 0 times 1 minus k 1 times theta 3 dot plus 4 omega 0 square k 1 times theta 1, 4 omega 0 square k 1 times theta 1, this equal to 0. So, this is the set of equations we get. Now, these equations, from here we can study the stability of the motion. So, once I will verify all these equations that somewhere some sign problem or other things has not taken place. Just quickly going through this part is ok, and 3 omega 0 square k 2 we have written as k 2 we have written I 1 minus I 3 by I 2, this is fine, and then theta 2, this equation is fine, and this equation just now we have derived, and theta 1 double dot, this is minus omega 0 1 minus k 1 theta 3 dot plus 4 omega 0 square k 1 times theta 1, where here itself we will write all those things. We pick up these terms, k 1 equal to I 2 minus I 3 by I 1, k 1 equal to I 2 minus I 3 divided by I 1, and k 2 equal to I 1 minus I 3 divided by I 2, I 1 minus I 3 divided by I 2. One minus k 1. So, k 1 is I 2 minus I 3 divided by I 2, this is fine, plus 4 omega 0 square k theta 1. Okay. And theta 3 double dot plus omega 0 theta 1 dot 1 minus k 3 omega 0 square k 3 theta 3. So, this is the final equations we are getting. This equation is very easy to analyze, the pitch equation. So, why we are calling this as the pitch equation, and it is a decoupled from the other the two equations. The reason is that once the satellite is going into the orbit, this is your E 0 1 direction, here you have E 0 3, and into the phase this is E 0 2. So, as you know, the velocity vector is along this direction, velocity vector of the satellite, and this is the circular orbit, circular orbit. Okay. So, using the right hand rule, if your velocity vector is along this direction, so using the right hand rule, okay, I can show it like this. Okay. See, it is passing over this blue line. So, this is the anti-clockwise motion and this is the roll motion. Similarly, the motion about this axis, the third axis. So, it will be going something like this. Okay, it is passing over the blue lines, means I am doing like this. So, this is also a positive motion and this is called the yaw motion. This is the yaw. Okay, now what is the pitch? So, about the third axis we are taking the yaw, about this we are taking this as the roll, and about the two axis. So, two axis, how the two axis is going into the page, it is going directly inside the page. So, this is something like it is a nose up motion. Okay. If I draw this E 2 direction, say if I write here as E 1, this is E 2 and vertically down this is E 3. So, this is E 0 1, E 0 3 and this is E 0 2. So, motion about this axis so, this is passing from the below, okay, and here it is like this. Wherever it is the green line is visible, means the your red line, this pink line is going below that. Okay. So, in this direction this is the pitch motion. Generally the pitch motion is about the roll motion is this notation is coming from the aircraft, and as I have told you, along the velocity direction we take this as the roll, and then along the y direction we take this as the pitch. So, this is acting as a y direction. So, here roll will be along this direction, and how the roll will be, it is going like this. So, here again you see the green line is below the red line, okay, here in this place, and Z 1 is also like this as shown here in this place. So, this pitching motion equation, if the body is slightly perturbed from the this orbital axis, means this is your orbital axis system E 0 3, E 0 2, E 0 1, and body is slightly perturbed from this position, little bit of perturbation, okay, not large. Here it is looking large, but this angle is, these angles are small. So, that the linearization remains valid. So, little bit of perturbation. So, in that case you can see that this line still it is near this line, this line is still near this line, this line is still near this line. Okay. So, the motion about this blue line I can consider this as the pitch motion, about this line I can consider this as the roll motion, and about this line I can consider as the yaw motion. Okay. While actually we have defined the roll along this, pitch along this, and the yaw along this. But it so happens that whenever you take the case of the aircraft, so in the aircraft we fix up the three body axis. This is the x b axis, this is the y b axis, and z b axis it is a pointing downward. So, the motion about this, it is a consider the roll about this body axis. So, in fact, this roll, pitch, yaw, whatever we say, these motions are about the body axis system. But here it so happens that the body axis and the orbital axis, they are quite near to each other, and therefore, I am telling that this is the roll, this is the pitching motion, and then the yawing motion. Okay. So, similarly, here in this place, this will be your pitch, this is roll, and the yaw using the right hand rule. So, yaw is like this. So, this is your yaw. So, this is the case of the aircraft, and your velocity vector direction, let us assume that this is lying along the same direction. Okay. So, from there I have described this notion that how the roll, pitch, and yaw they are related. but consider that the body axis are coinciding with the orbital axis itself, and body is just rotating about the E2 axis, EO2, that is it is just rotating about this axis. So, there is just the pitching motion involved, is not it, and if I disturb the satellite by small angles along the all the three directions. So, how the behavior of the satellite its motion can be described. So, that is about the spin stabilization. We will come to this is a separate topic which we will take up later on. So, right now we are concerned about the gravity gradient problem. So, here what we have observed that this is my pitching motion. Now, you can understand that why I am telling this is the pitching motion, because your theta 2 you are writing along this direction, theta 2 dot, this is your theta 2 dot. So, approximately this is valid. Okay. Now, this part and this part, this is the roll part and this is the yaw part, this is the yaw part and this is the roll part. So, what we see that these two equations are coupled together, because theta 1 appears here. So, theta 1 also appears here in this place, theta 3 appears here. So, it also appears here in this place. So, these two equations are not independent of each other, they are related to each other, and in fact, I can take double derivative of this equation. Okay. So, theta 1 so, here if I take the double derivative. So, theta through the there will be 4 dots over theta 1. So, this means we can write this as like this. Okay. This is theta 1 and then 4 dot, this is 4 here, okay. D to the power 4 here like this. So, this is the fourth order differentiation. Now, if we do this kind of things, so here you will see that theta 3 double dot will appear in this place, here theta 3 triple dot it will become, and here this will become theta 1 double dot. Okay. So, we can utilize, we can differentiate this particular one once. So, theta 3 triple dot it will become, I can insert here. So, this way I can eliminate this, but it is a much easier to do in terms of Laplace transform. So, these two equations I will do it in terms of Laplace transform rather than stretching in terms of the differential equation, and this part we can take up separately. So, first of all let us take this pitching motion equation. So, our pitching motion equation is theta 2 double dot plus 3 omega 0 square k 2 times theta 2 plus 3 omega 0 square k 2 times theta 2, this equal to 0. And if you remember, then this just is similar to spring mass system. So, this implies that this will continuously, if we are looking for stability of this kind of system. So, we must have 3 omega 0 square times k 2 greater than 0, and this quantity is always positive. So, therefore, this implies that k 2 should be greater than 0. And what does it mean? The k 2, the quantity we have written on the previous page, k 2 is I 1 minus I 3 divided by I 2, I 1 minus I 3 divided by I 2, this is k 2. So, this quantity should be greater than 0. So, this says that I 1 should be greater than I 3. In another way, we can write this as I, this is 1 which is related to the roll. So, I roll is greater than I yaw. Okay. This quantity must be satisfied. That means, the moment of inertia about the roll axis should be greater than moment of inertia about the yaw axis. Okay. Next, we pick up the other equations. these two equations, then we have to copy on the next page. So, the first equation we have, see here on the computer it is a pretty difficult copying from one place to another place. On the page paper it is very easy. Whatever I write here on one page, I can directly show you, that here I have to go back and forth again and again. So, for not creating any confusion, so I am wiping out all these things. Okay, so this is fine. So, theta 1 double dot minus omega 0 1 minus k 1 minus k 1 times theta 3 dot plus 4 omega 0 square k 1 theta 1, 4 omega 0 square k 1 times theta 1. So, this equation I have written here, and the other equation also I will copy, theta 3 double dot and then plus omega 0 1 minus k 3 times theta 1 dot plus omega 0 1 minus k 3 times theta 1 dot and plus omega 0 square k 3 times theta 3. This equal to 0, this equal to 0. So, these are the two equations where ROL are coupled. Now, I do the Laplace transform of this. So, Laplace transform of this will be s square. Instead of writing theta s, I will just write it as theta 1. So, understand that this is the Laplace transform. Okay. Omega 0 times 1 minus k 1, then s times theta 3 plus 4 omega 0 square k 1 times theta 1. So, these are all theta 1 here I am writing. So, this is nothing but theta 1 s, it is a function of s. So, this is Laplace transform. Similarly, this we have to do the transform s square theta 3 plus omega 0 times 1 minus k 3 times s theta 1 plus omega 0 square. So, these are the two equations which is Laplace transformed and obtained from these two equations. So, as I have told you that I could have double differentiated this equation and then inserted from this equation to get a single equation, and I could have eliminated this theta 3 dot from this place. Okay. And we will get a quartic equation, means of the differential equation of order 4 in theta 1, but instead of doing that, what we are doing, that we have Laplace transformed. Okay. And you can see that theta 1, theta 3, all these are appearing. So, this in the combined equation we can write this in the matrix notation. So, one step I will have to go more and combine the terms. So, if we combine, we can write here on this side itself. So, you look here in this place, this is theta 1 is here, theta 1 is here. So, we can write this as s square plus 4 omega 0 square k 1 times theta 1 minus omega 0 1 minus k 1 times s I will put here in the beginning, this is s, here theta 3, this equal to 0, and again picking up this one. So, here theta 3 is here, theta 3 is here. So, this becomes s square. So, that term is related to theta 3. So, first I will write the term for the theta 1. So, this is the theta 1 term. This is omega 0 1 minus k 3 s times theta 1. So, theta 1 will put here, s I will put here, and then the other terms which is plus s square plus omega 0 square k 3 times theta 3, this equal to 0. And this can be written in a matrix format as s square plus 4 omega 0 square k 1 and then s times omega 0 1 minus k 3, and here similarly we have s times omega 0 1 minus k 1 and this particular term s square plus omega 0 square k 3. So, these are the terms, and this is operated on theta 1, theta 3, and this equal to 0 0. Okay. Right hand side we do not have place, so I have written it here. Okay. Now, for the non-trivial solution, its a determinant must be 0. Okay. So, on the 5th page we have. So, for its determinant to be 0, so s square plus 4 omega 0 square square k 1 minus omega 0 s times 1 minus k 1 is fine, and then s times omega 0 1 minus k 3 s square omega 0 square k 3. Okay. So, we must have for non-trivial solution s square plus 4 omega 0 square k 1 and here omega 0 times 1 minus k 3 s 1 minus k 1 times s plus s square plus omega 0 square k 3. Okay. So, this determinant this has to be set to 0 for the non-trivial solution. I hope you are aware of all these properties of the matrix, because this is the preliminary requirement for this case, this course. Okay. So, the quantity s square plus omega 0 square k 3 and then this becomes plus s square 1 minus k 1 times 1 minus k 3, this equal to 0. And we need to expand it and work it out. So, this quantity gives us s to the power 4 and plus omega 0 square k 3 times s square plus 4 omega 0 square k 1 times s square, and this one gives us 4 omega 0 to the power 4 k 1 times k 3, and from here we have omega 0 square s square, and this also we can expand it. So, this will be 1 minus k 1 minus k 3 plus k 1 times k 3 and this equal to 0. So, few more steps are required to get hold of all these things. Omega 0 square still we keep it like this, s square plus k 1 times k 3 and then expand it omega 0 square s square minus square k 1 times s square minus omega 0 square k 3 times s square plus omega 0 square k 1 k 3 times s square, this equal to 0. Now, what we can observe that can we simplify it? This is what we are looking for. So, we have here term like the 4 omega 0 square k 1 s square, and here this is omega 0 square k 1 s square. Also, if you look here in this place omega 0 square k 3 s square, here with minus sign, this is present. So, we can write this as s to the power 4 and omega 0 k 3 s square. So, this term will get cancelled, okay. And this term and this term, we can combine them together. So, this becomes 3 omega 0 square k 1 times s square okay. This is a constant term. Then we have this term present here, which is omega 0 square s square okay. And the last term which remains. So, these two we are combining here in this place, and the last term then remains is 4 omega 0 to the power 4 k 1 k 3 and we have one more term here. This term is remaining. So, this term also we put here in this place omega 0 square k 1 k 3 times s square, and this equal to 0. So, s to the power 4 plus omega 0 square we can take out from this place. This is omega 0 square, omega 0 square, omega 0 square, and the s square is also common. So, 3 this becomes omega 0 square, okay. Then 3 k 1 s square will be taking it outside, okay. This becomes 1, and here omega 0 s square goes outside. So, this is k 1 k 3, and here this is s square. In the last term we have to put here k 1 k 3, this equal to 0. Okay. So, to summarize, we can go on the maybe the next page and summarize this equation. So, what we are getting, the combined equation, it looks like this: omega 0 square 1 plus 3 k 1 plus k 1 k 3 times s square plus 4 omega 0 square times k 1 k 3, this equal to 0. And the roots of this equation will describe the system behavior. Okay, so, I am trying to wind it up. Now, if you look here in this equation, so for stability, it is required that one plus 3 k 1 plus k 3, this must be greater than 0, 4 omega 0 square k 1 times k 3, this should also be greater than 0. In addition, 1 plus 3 k 1 plus k 1 k 3 square minus 4 times 4 this term omega 0 square k 1 k 3, this should also be greater than 0. This you know very well that the coefficients of this polynomial in S, this must be positive. Okay, this quantity is positive. So, this must be positive if we do not want to have any roots in the right half complex plane. Okay. So, if so happens that the roots are in the right half complex plane, means the system becomes unstable. From the Descartes rule, you know that in any polynomial, the if we are writing it like this, say the polynomial is f x and you are writing here as x to the power n times say a 1 times x to the power n minus 1 and so on. Okay. So, the nth order polynomial. So, as many sign changes, so number of roots in the right half complex plane, it is bounded by the number of sign changes that takes place in the coefficient of this polynomial. This is the Descartes rule. But what we are looking for, that there should not be any root in the right half complex plane for the stability to be maintained. So, therefore, I do not want any sign change, means all these coefficients, this and this, they must be positive. Similarly, if we are looking for the roots in the left half complex plane, okay. So, what we will do? We will change this to the f minus x, okay. And so, the x here will be replaced by this minus x, and then we will look for how many sign changes are there. This is also part of the Descartes rule. So, that will tell you the what is the upper bound on the number of roots in the left half complex plane or the on the negative side. So, here it so happens that if you put here s equal to minus s, so only in these two places there is nothing changes here in this equation. So, this simply implies that if these are positive, so there is no roots in the left half complex plane. So, it is a purely imaginary roots exist in this case, and moreover this condition must be satisfied. You can check yourself by taking some simple example of this quartic form, okay, and then trying to find out the rules. So, if this quantity is not greater than 0, so your condition will not be satisfied for the stability, means we know here in this case that all the roots are purely imaginary, all the roots are purely imaginary. Okay, we can not take what I mean that here what we have written that s to the power 4, if I write the equation like this, b s square plus c. So, you can write s square equal to minus b plus minus b square minus 4 a c, and this is under root divided by 2. So, this is the part we are talking about. So, if this condition must be satisfied if we do not want any roots in the right half complex plane, and you can check using a very simple example for this. Okay. So, this 4 into 4, this is nothing but 16 here. So, in this place, so on the next page maybe we can write. So, in summary, for stability, this k 1 times k 3, this must be greater than 0, then 1 plus 3 k 1 plus k 1 times k 3, this must be greater than 0, and moreover this condition should also be satisfied, 1 plus 3 k 1 3 k 1 plus k 1 times k 3, this whole square must be greater than 16 omega 0 square. Okay, here we are missing this omega 0 part. So, omega 0 square. So, this is omega 0 we have picked up this part from here to here, omega 0 square is there. So, omega 0 we need to put here in this place, and somewhere we have missed some particular this square part. Here we have, here this is the 4 omega 0 to the power 4 k 1 k 3. So, this 4 we have missed, instead we have written here as 2. So, this is your 4. Okay. So, here this should be 4, and here also this should appear as 4. Okay. So, omega 0, this quantity is always a positive quantity. So, we can summarize like this: k 1 times k 3 should be greater than 0, 1 plus 3 k 1 times k 3, this should be greater than 0. And here if you look for this part, so this is omega, this also becomes omega to the power 4, and here there is omega to the power 4. So, this can get eliminated because it is a positive sign. So, positive quantity. So, thus we get that this quantity square should be greater than 16 k 1 k 3. This is 16 k 1 k 3. Okay. So, these are the conditions for to be satisfied for the stability. So, these are the condition. Now, we have to analyze it. Okay. We have got the condition that under this condition we get the purely imaginary roots, and based on this, how these conditions will help you in designing the spacecraft. And what is about the design? We want to choose the values of capital I 1, this is the, we want to choose the inertia matrix basically I 1, I 2, I 3. These are the things we want to choose. So, will it guide me in doing so? So, we will take up this problem in the next lecture, and for the time being, thank you very much for listening.